For graphs of motion, at school level, we're only going to worry about constant acceleration. So if ever you need to draw an acceleration time graph, it's going to have to be a flat straight line because we're only interested in constant acceleration. There might be some changes in direction, or perhaps there'll be a big change at some point and then it'll become negative or something like that. But your acceleration time graphs will always be straight horizontal lines because of the fact that it's always constant acceleration. So if acceleration is on the y-axis, let's say that's 9,8, the rest of this graph that doesn't exist then, it's always going to be 9,8 constant. If we're looking at a position time graph, we are taught that the gradient is equal to the velocity. Why is that? Position, remember, is the same as displacement, and we can represent that either with an S or with an X. If I want to say, what is gradient? Gradient is change in y over change in x, which is change in displacement over change in time, and that is equal to velocity. If I have got a constant position, in other words, I'm not moving, I'll get a horizontal straight line. So that is no velocity, zero velocity. I haven't moved. Then I could sit there and say, well, what about if I have a nice, neat straight line going up? I am going forwards, and I have constant, it's a constant gradient, so that's constant velocity, and it's positive. If for some reason I were to have a position time graph and my graph comes down like that, I have a negative constant velocity. And negative often just means in the opposite direction. So let's think about what this guy's done. He has gone forwards. In other words, he has had an increasing, he was 5 meters, 10 meters, 15 meters. Then he went from the 15 meter position to the 10 meter position to the 5 meter position back to the 0 meter position. So he basically went there and back. That's what's just happened. And finally, or not, sorry, not finally, there are two more. What if I have an increasing velocity? That would mean my gradient has to increase. So flat, slightly steeper, slightly steeper, slightly steeper, slightly steeper, slightly steeper. So if I get that type of a half hyperbola shape or an exponential shape, I have got an increasing velocity. And if I have got something that looks like this, where I start off with a steep slope, less steep, less steep, less steep, less steep, that is a decreasing velocity. If I now look at a velocity time graph, notice I'm measuring meters per second and time. Change in y over change in x is equal to acceleration. So the gradient is the acceleration. We are also taught that the area under is displacement. Let's think about area. Area is going to be length times breadth, so it's going to be equal to velocity times time, and velocity times time is equal to displacement. So that makes sense. Let's see what we're going to have in terms of the gradient of this graph. If my acceleration is constant, I am going to land up with a positive acceleration, will look like that. Positive, constant acceleration. And if I'm coming down in the opposite direction, negative, constant acceleration. Oh, sorry, that was it. That's an acceleration there. Constant acceleration. And if I land up with a straight flat line like this, then I have got zero acceleration, and I have got a constant velocity. The displacement, or the area underneath, if it was underneath this, I'd measure that rectangle over there. If it was underneath the triangular shape, I could say half the base times the perpendicular height and get the displacement. Let's look at an example. I've got x in meters over here, so that is a position time graph. And let's see, we've got two guys, let's say they're running. What does this tell me? Firstly, the one guy starts at 4, okay, and the other guy, L, starts at -5. So in other words, to start this journey, they are 9 meters apart. That's the difference in their positions. What happens to L? L makes some forward progress, and he gets to -2. What's happened over here? He has had a constant velocity, and I could work out that velocity using the gradient. He then stands still in a constant position for that entire part, and then he goes forwards again, and can you see the gradient's much steeper over here? So this is a greater constant velocity. Again, I can work that out from gradient. If I now take a look at K, K stays in one place. He stays at the 4 meter mark for 3 seconds. Then what happens is he moves in the opposite direction. So this is negative velocity, but the negativeness is meaning that it's going in the opposite direction, not that he's somehow undoing his journey or anything like that. So this is also a constant velocity, but in the opposite direction to L. And finally, he starts moving back in a forwards direction, the same direction as L had moved earlier, and that is a gradient, which, by the way, is exactly the same but in the opposite direction. Notice the rise over the run, 2 down, 2 across, 2 up, 2 across. So here again, it's a constant velocity, but it is a velocity in the opposite direction to between 3 and 8 seconds. So that is an example of a position time graph. If I were to get a velocity time, I could do something like that. We've talked about it. We have velocity increasing, constant acceleration, constant velocity, downward. We've got velocity decreasing, and it's a constant acceleration again. And at this point, he stops, changes direction, and goes under the line. And remember, we can always subtract that area if we are trying to calculate the displacement under that graph. Don't forget that if you are doing graphs of motion, we can also take a look at what happens with a ball that is, let's say, dropped. If I throw a ball into the air, and then that ball comes back down again, what is going to happen? Firstly, let's look at its acceleration time graph. The acceleration remains negative 9,8 meters per second squared. If I take a look at the velocity time graph, I get given a certain velocity to start. We've done this already in the last revision. Stop at a certain point up at the top there and continue in the opposite direction, coming back to the exact same position. So this area will be equal to that area over there. And finally, if I'm looking at displacement time, what is going to happen? I will slow down and then stop at the top and speed up. Notice the gradient goes from being steep to flat and from flat back down to steep. If I just drop the ball from the top down to the bottom, my displacement time graph would look like this. I would start with 0 velocity, and slowly my velocity would increase going up. So I would land up with a positive acceleration and an increasing velocity.